Hi, this is Giovanni Daprat speaking, and welcome to example 10. In case you have any question regarding the material in this example, please feel free to contact me anytime. Or if you want the data that I used to make the example, let me know. Okay, example 10 deals with this radial flow, which is in this case in a build-up test is missing. We will see the reasons. And again, objectives are determine well and reservoir parameters and limit nature, in this case ceiling or constant pressure. Well data and reservoir is here. You can read it. Uh, in this case, the regarding well data is limited entry. Uh, just 10 feet has been perforated. This is exploratory well, and in many cases, before you go completely or full perforation of the interval, you may just do a limited entry just to see to make sure that the reservoir is going to be commercial. Okay, regarding fluid data, this is, you can read it over here. Um, Specific gravity, gas oil ratio, and some of the like parameters like this one, formation volume factor, has been derived from correlation. In exploratory wells, in many cases, you don't have time to expect PVT analysis, so you may use the correlation. And for that, you need your initial pressure and temperature and the API that you may get using these correlations, what you need to make calculations for the well testing. So this is the story, the test history, bottom hole pressure and surface rates, the history plot. We got drawdowns or production periods and a buildup. Before this, there was a cleaning phase. After the first buildup, which objective is probably to get the pressure, the initial pressure, there is another production period, and you have different, let's say, probably we use different choke size here, and the final buildup. Okay, if we go now, what we're going to do is to apply the load log diagnostic plot to all the build-up periods, in this case are two, and we realize here that there is no evidence of radial flow. Let's say this is a change in well storage situation, so radial flow should be expected. Let's say this is the final well storage, and then one, according to the classical rule, the log and a half rule, you should expect radial flow around here. But you can see here that derivative is not has not that tendency to become flat or no slope, zero slope. So there is no evidence of radial flow here. If you try to use log and a half rule and trying to infer here your value of permeability, probably is wrong. It's going to be lower than the actually what it is, as we will be seeing. So this is build-up 1, this is build-up 2, and we realize an inspection using flow regime diagnostic that this is the slope here is minus 1/2, which means a spherical flow, which is, let's say, expected because we got 30 feet thickness and we just perforated 10 feet. So you may expect here spherical flow, but after that you should go to a transition after spherical flow to radial flow, which is not seen here. Let's take the second build-up. You have spherical flow due to limited entry, created by limited entry. Then after that you should go and have your radial flow around here, but you can see here that the tendency is to keep declining, probably due to a constant pressure or a sealing boundary or some discontinuity that makes the pressure to keep constant. So let's go now to the drawdown periods. In this case, drawdown, if it is very clean data, you can use them also besides the buildup. And we can see here that there is no evidence, at least that during this testing time, 10, 20, almost 29, 26 hours, there is no tendency to the pressure to keep constant. If we have a constant limit, no matter if there is a buildup or drawdown, pressure is going to the trend should be to be a constant value, and therefore the derivative keep declining or going down. So according to the drawdown periods, there is no evidence or tendency during this testing time. Again, if the testing time is longer, maybe over here, then you go down. This could be a discontinuity, and then eventually the pressure is going to go down according to the limit, assuming a constant pressure limit. That's one of the interesting things about that we will see later on about the deconvolved pressure that is going to be like an extended drawdown, and we'll see the benefits here. Okay, let's have a look at the first drawdown period after the initial buildup. We can see here quite similar behavior with the buildup, at least over here is a -1 slope, indicative of spherical flow. And then we may say probably according to what is expected from a limited entry well, this part here, zero slope, should be indicative of a radial flow. Okay, then what we do now is to apply several reservoir models. I'll show you later using the software Sapphire that we got another model, but for in this what we see here is not shown. We'll see it later. So a match is obtained using a homogeneous model and a limited entry well located in a block with sealing boundaries. You can see here now the match using the model. This is changing wellbore storage. Then here is the spherical flow, and then eventually you don't see the radial flow over here because the superposition, the impact of the limits does not lead to develop. So just go because of limits effect. Now we do the simulation, and you know that once you do this one event analysis, could be a build-up, could be a drawdown. What you have to do is to construct the whole or simulate the whole pressure history, as we see here. And here we may say that it's a good example to apply the deconvolution method using both build-ups. And this is the deconvolved pressure that you see here. And again, the model is the same that we used for in the last build-up. Limited entry well located in a rectangle type of limit, with all sealing boundaries. Here you can see the -1/2 slope, and then the deconvolved pressure has the advantage to be around 200 over 200 hours compared with the almost 30 hours drawdowns duration. So this allowed us to confirm this is, let's say, a drawdown, a constant rate drawdown, and the slope here is 1, which is the indicative of pseudo-steady state. So we reach the limit, and should be a closed boundary type of limit. So we did the simulation, and both, even using the one event or the build-up analysis or the convolution, are the same. And these are the numerical results, which is basically both are the same. Instead of 10 as physically perforated according to the logs, this simulation gives us 7 feet that has been the perforated length. You see perforated length, it's a parameter you can regress, enter in regression until you get a good match. Permeability around 13 millidarcy. Other things are, and these are the distance to the limit. South, where south, east, northwest is a reference. And another information regarding stock tank oil in place. So conclusions, based on log diagnostic plots applied to buildup periods, no radial flow was identified. Instead, a spherical flow associated to a limited entry well condition, followed by a decline in the derivative due to impact or superposition of a sea limit, which did not allow radial flow to fully develop. There are many cases like this in practice. So, but again, in many cases, you tend to believe that this pressure maintenance is due to a constant pressure limit, like a huge aquifer, and you have to check the drawdowns to make sure that they're both in line regarding the limit, like we're saying here. Log diagnostic plot applied to the drawdown period. The derivative trend shown during the drawdown time is not indicative of a pressure support type of limit. Limitation is the time of the drawdowns, 20 hours, 9, 30 hours. And here is the benefit of the deconvolved pressure, 225 hours. Confirm preliminary diagnostic based on drawdown analysis. Limit is a rectangle with all sides of a ceiling type. So a conclusion derived from this example is that the analysis of drawdown periods, if pressure data quality is good. In many cases, you don't even have the pressure data. Therefore, tendency has been to use build-up because the data is clean, because the data is more practical, let's say, to analyze. And nowadays, machine learning, you can see that in the case of permanent downhole gauges, you have a lot, millions of data, drawdown data actually, and in that case, okay, pretty sure the drawdown periods and buildups are analyzed. And as said before, the deconvolved pressure could be seen like an extended drawdown. Okay, let's go now to recreate what we did with the software. Here it is, we're gonna be very, let's say, play very informal with this. We can stay 1 hour or two just enjoying the analysis, but I just want you to show what the results are coming from using the software. So this is our data. Then what you do here is you enter extract delta P, and you choose what period to analyze. You can choose this, or if you want, you can even choose all the events. And you're gonna have here something like this. Let's expand a little bit. And here is, if you do this, and again, if the data quality of the drawdowns is good or has been acquired, then you can see here that this tendency during the buildup of a pressure maintenance like here is not due to a constant pressure support, because the drawdowns, which are this one here, are not, even if we extend it, then it seems that if it is the case of a constant pressure, both drawdown and build-up pressure should be trying to stabilize. So one, let's show now two two events. One event is let's see here, production to 1, and you see here this is this drawdown here, um, like the buildup that we will see in a while. Uh, Here is the spherical flow. Let's show some tools. This tool here allows to is just to show you where minus one half slope is, and you can see here very clear that this is minus one half, and you are tempted to say, well, probably this is radial flow too. Um, Okay, so if you do this, by the way, according to this software, you can get the results in plot regarding what is related to this spherical flow, like spherical permeability, anisotropy. One idea of permeability too, assuming the boundary is infinite, that should be this one here, which is this given, this value is given by this line here. If we probably try to fix it over here, you will see that if this is radial flow, the value should be this one here. So let's go now to our buildup. This is changing wellbore storage, and let's now go and see what we did here in the what we use for the analysis, because the buildup is the time is quite is longer than the drawdown. So this is our buildup here. Let's take out this for a moment. And again, you can check here that this is the spherical flow down here. We can even zoom if you like for a better definition. And you can see that some points are here. But probably you should expect radial flow over here, but it's not shown. But if there was, if the effect of the seal boundary or pressure trying to stabilize, and this is the reason that you don't see it, the radial flow over here. So what we did here is to try different models. I would like to show you. We're not going to do this because it's going to take time. And but you can see here we tried with this. Initially, we tried with this model here, which is a radial a limited entry plus radial composite model, and we did several runs with this, applying nonlinear regression. But you can see here that there is a tendency here which does not follow the data. We can compare it with our final, which is the one that we decided to use. And you see here that radial composite type of reservoir, and this is the homogeneous solution. The homogeneous one is more representative. On the top of that, when you have radial composite reservoir, you should assume that at some distance there is a change in mobility. This type of thing, in many cases, is expected when you have a water injection, or you have a change in the mobility, or you have gas condensate, which condensate and gas are close to the well, or there is a radius, let's say, a composite radius with condensate and gas, and then as as far you move from the well, only gas, and therefore the radial composite apply. But anyway, just to show you that mathematically speaking, uh, you can get simulation, but your data simulator, but here is not easy. On the top of that, we go to the semi-log, and you see there is no fit, no good fit, and also in the uh, simulation of the whole test history. Um, you can play and use, let's say, more things like a scheme dependent on time, and then probably you're gonna get a good fit here. But in this case, you have to also to integrate information, like I said, the composite, radial composite uh, means that that well, at some point, there is a change in mobility. This is a exploratory well, so there is no water injection or secondary recovery that I expect a change in mobility at some point. So therefore, we decided to go with the final, which is the, as I mentioned in the presentation, is the limited entry well in a closed rectangle with the sides. Let's see, let's go here to results, and you can see in the results. Let's go to the reservoir and boundary. These are the limits, let's say the distance, 800 feet, 650, so, and then 1,000, 1,200. Also, you can compute your geometrical scheme, which is 15.9. This is for the limited entry, which is normally a calculation that can be done. Okay, so let's let's go now again back to our presentation, and this this is finished. Let's see. So thank you for your time, and hope you have any questions. Please do not hesitate to contact me. Uh, and thank you very much again for your time.